Alright guys, this video today is about the pH scale, which is topic 8.3 in the IB curriculum. And the pH scale is a scale that's used to distinguish between acidic, neutral, and basic solutions. So, looking a little bit deeper into what the IB expects, we're going to be dealing with these two equations today. The equation that allows you to calculate pH from the concentration of hydrogen ions, and then the rearranged version of that allows you to find the concentration of hydrogen ions from the pH. Okay, and you'll notice this formula right here. It tells us that pH is a logarithmic scale, which means that every change of 1 unit in pH represents a 10-fold change in the concentration of hydrogen ions. Okay, and then these values that we use can help us distinguish between acidic, neutral, and basic solutions. We're also going to talk about an equilibrium constant specific to water, so the ionic product constant of water, or the Kw. And we'll be working with those equations that relate pH and the concentration of hydronium, as well as an equation that relates the concentration of hydrogen and the concentration of hydroxide. Okay, that'll be the Kw. You can see that over here. I will also touch on some other things that you wouldn't necessarily need to know for an IB exam. I'll talk briefly about pOH, and also it says here that you only need to focus on strong acids, but I will make a mention of what a weak acid might look like here as well. Okay, so let's get into it. So first here, I just have this very pretty graphic that shows us some universal indicator paper. And you can see that universal indicator is very useful because it's a different color depending on the pH of a solution. So a lot of the indicators you've already worked with are either one color in an acid and a different color in a base. So for example, bromothiamyl blue is yellow in an acid, blue in a base. And if you have a perfectly neutral solution, you'll hopefully get a nice green color. Okay, or phenolphthalein is colorless in an acid, and then if you get to a pH of about 8, it turns into this nice bright pink color. Universal indicator, though, it makes this nice rainbow, and the color tells us the pH of the solution, and that's because it's actually a mixture of different indicators, which allows for this sort of variation in color across the pH scale. Okay, and just a reminder, if you don't remember from grade 10 chemistry, that a low pH corresponds to an acidic solution. A pH 7 is considered neutral, and then a high pH is considered a basic solution. Okay, so pH, it actually means something. The P is for power of hydrogen. Okay, and the pH is determined from the concentration of hydrogen ions in solution. You'll remember that an acid is characterized by having a high concentration of hydrogen ions. So the pH is calculated as the negative log of the concentration of hydrogen. You're also probably, if you're thinking about the numbers a little bit here, usually we talk about the pH scale being from 0 to 14, but we can actually get values outside of that range. For example, if you have a really concentrated acid, then you might actually have a negative pH, right? If the concentration of hydrogen ions is higher than 1, you're going to end up with a negative pH here. Similarly, if you have an incredibly small concentration of hydrogen ions, for example, if you were dealing with a solution that doesn't have water as the solvent, then you could end up with a pH higher than 14. Those aren't examples that are going to come up for us, but just know that they are possible. We're not restricted to that 0 to 14 range. Now, this formula can be rearranged. If, say, I was given the pH of the solution, but it's more useful for me to know the concentration of hydrogen ions, I could use the rearranged version of the formula to get that concentration of hydrogen ions out of it. Okay, and hopefully you remember from math how to convert between these two. If not, though, I don't think I need to go over it right now. Okay, so we'll start with a pretty straightforward example. The pH of a 0.1 mole per liter solution of HCl, or hydrochloric acid. So, hydrochloric acid, so this is the formula we're going to be working with because we want to find pH. And hydrochloric acid is a strong acid, which means that 100% of my HCl molecules are going to break apart in solution and form H plus ions and Cl minus. But what I want to take from that is that there's a 1-to-1 ratio. I can say that if I have a 0.1 mole per liter solution of HCl, that means that I have 0.1 moles per liter of hydrogen ions in my solution. Okay, so I can put this number directly into my pH calculation. From there, I just throw my numbers into my calculator, take the negative log of 0.1, and I end up with a pH of 1. Now you might be wondering a little bit about the significant digits here. This is intentional to have 2 decimals after the 1 digit because I'm using a logarithm to calculate this value, so I'm using a kind of newer type of operation. You might recall that in a logarithm, the number to the left of the decimal, so like the 1 in this case, comes from the exponent, which means that it actually doesn't count as significant. So anytime we're calculating a value from a logarithm, any digits to the left of the decimal place, they don't count as significant. It's only the digits following the decimal that count as significant. So I had 2 significant digits here. That means I need 2 digits following the decimal here, which is why I wrote it as 1.00. Now moving forward, there's going to be a few more worked examples here. It's not a bad idea to have a piece of paper and pause the video periodically and try them out on your own, or you can wait to the end and revisit the worked examples when you try the practice questions. Okay, example 2. So this time I'm going to ask you to calculate the pH of a 1.0 mole per liter solution, but this time it's acetic acid, which is a weak acid. So delving a little more into that detail, or that idea of a weak acid, in a strong acid, all of the acid molecules break apart to make hydrogen ions in solution. In a weak acid, only some of them do. In the case of acetic acid, only about 1%. So if I want to figure out the concentration of H plus here, I need to take 1% of the original concentration of the acid. Okay, and 1% of 1 is 0.01 moles per liter. Once I figured that piece out, pretty straightforward, same steps as before, throw the pH, or throw that concentration into my pH formula, type the numbers into a calculator, I end up with a pH of 2, and then once again following that rule about significant digits, I have 2 significant digits on this number, which means that I need 2 digits following the decimal on my pH. Example 3. Just sort of a conceptual question, which is more acidic, a solution with a pH of 1 or pH of 2? How much more acidic? So maybe take a think about that. But hopefully it's pretty clear that the lower the pH, the more acidic. Okay, so a pH of 1 is definitely more acidic than a pH of 2. And the way the pH scale works is every time you change by 1 unit, you're changing the concentration 10-fold. So a solution with a pH of 1 is 10 times more acidic than a solution with a pH of 2, meaning its concentration of hydrogen ions is 10 times higher. Okay, next idea here is the ionization of water. So if you have a glass of water, pure water, no other ions dissolved in it, sitting on the counter, naturally this is happening all the time. So 2 water molecules right here will bump into each other. One of the water molecules will steal a hydrogen ion from the other, and you end up with this ionization happening. Okay? Now, you'll notice this is an equilibrium. So that forwards process that I described happens, but the reverse can also happen and is happening constantly, where the hydronium ions can meet up with hydroxide ions and reform water molecules. So if I wanted to write the equilibrium law expression for this, I know it's been a while, you can go back and review what that looks like. But just remember that equilibrium law is concentration of products over concentration of reactants, and if I have coefficients, I throw those in as exponents in my equilibrium law. For this specific reaction, my equilibrium law looks like this. Okay, so I have my concentration of hydronium ions times my concentration of hydroxide. You'll notice though I left the water part out. I don't have anything in the denominator here. And that's because water, in this case, is a pure liquid. Its concentration is constant, so I don't need to include it. Now this equilibrium constant right here, this K, actually gets a special name. It gets this little W subscript. It's the dissociation or the ionization constant for water. And it's a pretty important value in analytical chemistry. Okay. Now, thinking a little bit about what this value means. So the Kw is the product of the concentration of these two things. My question for you is it large or is it small, and how do you know? And if you think about water, our experience with water, you might remember two things. One, water tastes pretty nice and neutral and bland. It's not very sour. It's not very bitter. Also, pure water with nothing dissolved in it is not a good conductor of electricity. And those two facts tell us that probably the Kw is quite small, okay? Because it's calculated from two concentrations that are also quite small. Okay, and what's true, Kw, it's a constant, and at 25 degrees Celsius, it's 1 times 10 to the negative 14, so it's a very, very small number. Okay, and what this tells us, or what we can sort of infer from this, is that if you have a sample of pure water, distilled water, most of the water particles are not dissociated, okay? Most of them are not ionized. You have a very small concentration of ions, and that is one of the reasons why pure water does not conduct electricity very well. Now, in any solution where water is the solvent, you're going to have some concentration of hydronium and some concentration of hydroxide, but the relative concentrations determine if the solution is acidic or basic. So in a neutral solution, you've got equal concentrations of hydronium and hydroxide. In an acidic solution, a higher relative concentration of hydronium, or H+. And in a basic solution, you've got a higher relative concentration of hydroxide. Now, a little bit of analysis we could do with this idea. So the Kw is 1 times 10 to the negative 14. We could actually use that to figure out the concentrations of hydrogen ions and hydroxide ions in pure water. Okay, so I have this Kw expression that I came up with, remembering that H+ and H3O+, we can use those interchangeably. They mean pretty much the same thing. Now, I know that in a pure solution, neutral solution, these two are equal. I also know that Kw is this value that I've listed at the top here, so I can rewrite this formula making some substitutions. Okay, so it's a neutral solution. These two concentrations are equal, so I've called them both x, simplified that to x squared. Then I've put this in. I can solve for x here by taking the square root, and I end up with 1 times 10 to the negative 7. So the concentrations here of hydrogen ions and hydroxide are both 1 times 10 to the negative 7. One more step we can do with that is to figure out the pH of pure water, okay? The pH is calculated as the negative log of the concentration of H+. Throw this in there, and I end up with a pH of 7, which hopefully matches with what you've learned previously. A neutral solution has a pH of 7. Okay, this is example 4. We've got a sample of blood. It's got a concentration of hydrogen ions given. I want to find the molar concentration of OH minus, and then decide if the sample is acidic, basic, or neutral. However, my screencast program is going to time out, so I'm going to take a pause here, and I'm going to start up a second part of the video where we can look at example 4 in a little more detail. Thanks so much for watching, and I'll see you in part 2.